Hello, everyone, and welcome to this Flexible Circuit Technologies webinar. My name is Katie, and I will be your Global Spec moderator. All right, so today we have all of our participants listed on this slide here. So we've got Mark, Chris, and Ray, who are all going to be joining us for our presentation today. So I'd like to introduce our main presenters for today. With us today, we have Mark Finstad. Mark has over 40 years of experience designing flexible circuits and flexible heaters. He is the vice chair of the IPC Flexible Circuits Committee. Joining him today, we have Chris Clark. Chris has spent the last 35 years of his career designing and building flexible circuits. He is CID certified and sits on a number of committees. To kick things off today, I'm going to pass things over to Ray Contrell. Ray is the Executive Vice President of Business Development. So Ray, I'm going to pass things over to you. Go right ahead.
Katie, thank you, and good morning, good afternoon, and good evening to everyone. We truly appreciate your spending a little bit of your time with us today. We have a global audience, and your time is truly appreciated. Before I turn it over to Mark and Chris and their nearly 80 years of combined flex heater design expertise, we wanted to just provide a little bit of additional color on flexible circuit technologies, or FCT. Having spent 25 years in the industry, we've been part of your flex solution for greater than 2 decades at this point. So in addition to the industry-leading flex design services that we offer and an amazing team, we also offer in-house flex circuits, rigid flex, of course, flexible heaters, which we'll spend a great deal of time on today, flat flex, membrane switches, and more value-add advanced contract manufacturing for FPCAs, PCBAs, subassembly, and up to full box builds. We have a sterilization group for injection molding as well, really focused on medical products, but also offering that service to other industries as well. With our growth came a number of challenges, but all under the FCT, or Flexible Circuit Technologies umbrella. We branded our truly state-of-the-art bare circuit facility as FCT. I'll highlight that in the next slide as well. And under Inflex, our integrator of flexible solution, that's our EMS group. And we offer a remarkable broad range of EMS services from, again, PCBAs through subassembly and full box builds. And then within SteriMed, that is our plastic moldings group that is focused on medical, offering EO sterilization. I'm going to highlight just a few of our amazing world-class and state-of-the-art facilities that we've invested just north of $80 million in over the last 3 years. These facilities are in China today, just outside of Hong Kong. Hong Kong, we have Zhuhai, which is 500,000 square feet of advanced bare circuit manufacturing. And then Inflex, our latest offering at the beginning of last year, that campus is growing 900,000 square feet to date and offering full suite of EMS electronics contract manufacturing services. Chris, Mark, and I are at our Minneapolis office here in the US, but with some risk mitigation plans in place, we are also looking at offering Thailand from an EMS offering sometime later in Q4. So within our ecosystem, as Chris and Mark again walk through flexible heater design today, we offer a broad swath of flexible design services and offerings. In addition to that, we complement that with, again, our Inflex value-add advanced electronics contract manufacturing. So you can engage with us on the front end of your product life cycle, just on the design for flexible services or solutions, or come to us straight for electronics contract manufacturing. It's really trying to bring a variety of services to you throughout the product's life cycle. To support that endeavor, we have Asia-based commercial teams, as well as in Latin America, Europe, and North America. So for any of your immediate questions or comments or concerns on programs or your flex design needs, we have some type of representation within the region to support you better moving forward. With many markets that, again, Chris and Mark will highlight here in a moment, we have a host of accreditations and certifications to support those. To name drop on a few market segments, medical is big, automotive, EV, battery, consumer, and high reliability manufacturing. As Mark and Chris talk about all of the heater capabilities and services that we can provide from a design standpoint, including CAD, we have developed and designed thousands of different products for a variety of markets over the years. And one interesting thing that we've noticed recently is we're able to get product to the market in your hands in a quick fashion within weeks compared to some of our competitors, even in North America and Asia. We understand the need for new product development, and our team will support fast turns within weeks to get you to market faster. So in summary, FCT, Inflex, and our greater team can bring value to you again throughout the product's life cycle, from the initial napkin design through product cost downs at the tail end of a product's life cycle, offering a variety of services throughout and supply chain solutions to meet your cost needs. So at this point, I'm going to turn it over to Mark and Chris. In addition to our design expertise amongst those two gentlemen, we have a host of other application engineers that all come with 35 to 40 years of design expertise to really support you on the challenging solutions that you're looking for today. So this time, Chris, I would like to turn it back over to you.
All right, thanks, Ray. And hello, everybody. So for an agenda today, I'm going to cover typical applications and market segments that we see, some advantages of flexible heaters and why you would want to use them. And then I'm going to turn it over to Mark Finstead, and he's going to talk about some of the limitations of flexible heaters and design considerations. So some of the most common applications or markets that we deal with are, the big ones are obviously medical and automotive, but we also do a fair amount in aerospace, specifically aircraft, commercial aircraft. And then we do a fair amount of industrial and commercial applications as well. And we're going to cover each of these in a little bit more detail here. If we look at heater applications within the medical market itself, some of the most common is diagnostic. Another one is IV fluid heating. This could be the bags or the lines. It's been proven that if a patient or victim is in shock or going into shock, putting cold fluids in them doesn't necessarily give you the best care. And then just general patient care, and then also veterinary diagnostic equipment as well. If we look at diagnostic equipment in a little bit more detail, certainly PCR testing is one of the most common ones. It was common already, and then COVID came along, and in 2020 that market really blew up. So our flexible heaters allow you to have a high wattage heater that gets a patient a result quicker. Typically, these heaters range from an operating temp of 45 C to 98 C, depending on which stage it's at and which cycle it's in. But ultimately, this gives you reduced cycle time, which is faster results, and then more throughput for the care facility or hospital or clinic. And as these devices have become smaller and our heaters have become smaller, you end up with a smaller footprint. So you go back a decade or more, and typically this equipment was in hospitals or testing facilities, and now there's a lot of point of care, benchtop type applications in clinics or minute clinics. Patient comfort, I talked a little bit about the IV fluid heating. Typically these would be in like ambulances or possibly a field medic in a military situation where they're allowed to preheat these fluids before they go into the patient. Another one could be heated blankets, so heated blankets themselves, or possibly a blanket warmer. These would be in care facilities, giving people care where they get warm blankets and help prevent shock, or possibly infant care. And then much the same with IV, it's kind of been determined or found that if you warm oxygen before it enters the body, that performs a better response as well. And then veterinary care. So, much as the technology around human medical care is advanced, it also has with veterinary care as well. So people are spending more and more money on their animals to help keep them healthy and help diagnose issues as they arrive. So this is both cats and dogs, and they might be testing for things like Lyme's disease, as that's become more and more common, heartworm, and then various other ailments, kidney dysfunctions, diabetes in different cats and dogs. And then a little more detail around automotive and aircraft. Some of the common things would be battery heating, de-icing, mirror anti-fog, cabin sensors, and then some external aircraft sensors. Automotive specifically, so the EV market has certainly been one of our bigger markets over the last 3-4 years. So not only our large format flexible circuits that we make, but we can also make heaters that can keep these batteries at their optimal performance temperature. This increases efficiency, age in charging, and helps the batteries last longer. So these are all key things. So like I said, we manufacture circuits that help monitor the circuit performance overall, but then also heaters that can help control that temperature. A camera de-icing for those of us like Mark and I that sit in Minnesota where, 7-8 months out of the year, we have the opportunity to see freezing rain or frost. Camera de-icing can be a big thing. So this allows the cameras to be maintained at a temperature just above freezing. And then similar to that would be anti-fog, where you're warming that lens to make sure that there's no fog on the camera as well. A new technology, cabin sensors. So this specific one is alcohol monitoring. So there's technology out there allowing for a car to monitor not only if somebody in the cabin has been consuming alcohol, but the driver himself and whether or not he or she is impaired beyond the limit to be able to drive that vehicle safely. And then steering wheel heaters and other heaters within the cab. And then if you switch over to aircraft, similar de-icing applications and anti-fog, but then an additional one would be food prep for passengers. So this would allow the cabin attendants to either warm food and heat it to serve it, or keep it warm once it's already warmed up. So this could be liquids or solids. And then some consumer and industrial applications that we have seen over the years, similar to the one I spoke about with aircraft, food and drink warming. This could be baby bottles or coffee warmers, vaping or tobacco use where they're warming or roasting tobaccos or chemicals, hand warmers in snowmobiles, ATVs, UTVs, even chainsaw handle heaters. We've seen applications for that. Different gloves and mittens, fluid warming. So any kind of fluid that you want to warm up to a certain temperature, typically that would be a body temp or just above, so it feels comfortable when it gets applied to the skin. A lot of cosmetic stuff out there that they see advantages to warming it. And then selective surface cleaning or de-icing or warming would be another one. Some of the advantages of flexible heaters. So the big thing here is these are custom. So you're not going on to Amazon or a catalog and buying a predetermined shape and size and a certain watt density. You can tell us exactly what you want for shape and size and what you need for a resistance or a watt density. And we custom design these heaters to be an exact fit for your application. They can be mounted on flat or curved surfaces, and they can be profiled. So within a single substrate, you may have one zone that you want to heat a little more for whatever reason, and we can adjust that heater pattern to allow for more heat or watt density in that certain region. We can also add temperature sensors and thermal protection, and there's multiple termination options which we will discuss in more detail here shortly. The big thing here is to get us involved early, and we can help you make the right solution. So if you come to us before these heaters are completely designed, we can help coach you and tell you whether or not you're headed down the right path and using the right components and materials. So if we look at installation methods in a little bit more detail, one of the common methods is just peel and stick. So we can put a pressure sensitive adhesive on the back of these heaters. And then when our customers get them, they just peel off the protective liner and stick them in their device. The other option would be where we pre-laminate those with a thermoset adhesive on a heat sink of your choice. Either we can source it or you can supply it. The advantage here is faster warm-up time, higher peel strength values, and a more intimate bond. So with PSA, you always have the risk of a small air pocket, which could create a hot spot. And then we can also put these on curved surfaces. So the previous slide here kind of illustrated a heater that's mounted to a heat sink that has a slight curve to it. And then these aren't really heaters, but another technology that exists is a Type T thermocouple flex circuit. So these use the same resistive foil that we commonly use in flexible heaters, but you're now able to create a Type T thermocouple where you have alternating patterns of either copper plated on top of that resistive foil, or you can actually create a two-layer circuit where you have a resistive foil on one surface and a copper surface on the other one, and then they're connected with a blind via typically. Reduced size versus a conventional wire thermocouple, and these operate in temperature ranges from -200 to 150 C. You have multiple termination options available with flexible heaters. So, pretty much anything you can do with a flexible circuit or a PCB, a traditional rigid PCB, you can do with a flexible heater. So this could be wired leads. If we look at the upper left image there, these are just wires that get soldered on. That particular example has potting over the leads to help protect them. Another common one is insulation displacement contacts, or IDC crimps. That's the picture in the lower left. So these can be male or female. They pierce through the flexible heater lead and connect to the traces, and then they can either be with or without housing. Connectors, these could be through holes or SMT connectors. The image on the right there is a through hole one, but again, any kind of connector you could put on a flex circuit, you can put on a flexible heater as well. We can just open up pads and ENIG plate them for you, or pre-solder them, and then you can solder wires of your own. Or another common one is the flex tail with a ZIF pattern. I don't know, I think about 80 or 90% of the designs I see nowadays have ZIFs, especially with flex circuits. And then temperature uniformity. So I had talked about profiling your heater element. So you can have it set up where you're going to have more or less heat in a certain region. Maybe it's it's going to cool faster. That could be a reason for that. Or like with PCR testing, oftentimes you want different zones to heat at different rates. So you can custom tailor the element to get exactly what you want. And then the ability to integrate temperature sensors and thermal protection. So we can put thermistors on these heaters. Often these are just SMT type chips that get put on with pick and place. So it's very cost effective and efficient. We can put RTDs on them. You can create zones with the Type T thermocouples like I had discussed a little bit ago there. Thermal fuses could be etched in or soldered on. Thermal cutoffs, and over the years, these have gotten to be where they can be resettable as well. So if it gets to a certain temperature, the device would shut off. Most commonly, they're just controlled with a controller circuit, but the option to add an extra layer of protection is there. We could put a thermostat on them, and then we could create dual elements for redundancy as well. And with that, I'm going to turn it over to Mark Finstead, and he's going to talk about flexible heater limitations.
Thanks, Chris. So Chris has gone over an awful lot of applications and different industries that flex circuits are used in, and it is important to recognize applications where a flexible heater is a good indicated for that application. And there's a few things here to be aware of. If you have very, very large heaters, things that are over about 36 square inches, They can be expensive. I'm going to be getting into cost drivers here a little bit, just a little bit down the road here. It's also important to understand the temperature limits of flex circuits. I'm also going to get into that. The materials we use are typically polyimide film, and those are very flexible, but they're not elastic. So it's important to keep in mind that they don't stretch. So you can wrap them really nicely around a single axis like a cylinder, but they don't fit well around something that's bowl-shaped. To do something like that, we would have to profile the outline of the heater to be more like a star shape, and that would allow us to conform to that. And we can certainly help you if you have a shape that is more than a single axis where you're trying to form the circuit. So when you have a new flex heater, the first question I'm going to ask is, what's your maximum operating temperature? And that's going to drive the type of adhesives that we use to bond everything together. And you can see that there's 3 different options that we currently have. And you'll notice that each one of them is designated at 0 power. And I'll get into that a little bit here in just a few minutes also. You probably also wonder why we wouldn't just make everything at the with the highest temperature level or temperature adhesive. The main reason is cost. As the temperature limits go up, so does the cost of the circuit. We want to give you the most cost-effective design that's going to give you a reliable heating solution.
Hey, Mark, a question came in. Why are they only suitable for static applications?
Well, the issue that we have with flex circuits in general is that when they heat up, the adhesives will tend to soften, and they can be, you're going to lose some of your bond strength. And if it's heated and moving at the same time, you can actually have delamination problems. And the majority of the heat, I'll be getting into this a little bit more as we go on, but the majority of the heat from a flexible heater is transferred through conduction. There's very little radiated or convection transfer. And so for that reason, virtually all the heaters that we build will have some type of adhesive on it so that they can be bonded to whatever object it is that you're trying to heat, because that's the most efficient way of transferring that heat to the object you want to heat. So anyway, our first option, that'll go up to about 125 C at 0 power. And the reason we say that is if you're heating something up to 125 C, that's your top target temperature, you have to remember that if you heat it up to 125 C and then shut it off, you're going to overshoot beyond that. And you want to make sure that you're not going to damage the heater by over-temping it. So the first one is a standard epoxy or thermosetting acrylic adhesive. This is the same stuff we use when we build our flexible circuits. And so it's very easy to process. It's the least expensive option, and we do a lot of heaters and flex with that. The next step up is we'll take you up to about 150 C at 0 power. And this is an enhanced thermoset adhesive that was actually designed originally to be a high-speed, low-loss adhesive that would be used in flexible circuits to replace things like liquid crystal polymer. And one of the side effects of their design was they ended up with an ultra-high bond strength. And because the bond strength is so high, it also is able to withstand higher continuous temperatures. We can take that up to 150 C without any issues. For very high temperature, we can go up to 200 C with thermoplastic polyimide. And that's going to be more difficult to process. You have to have a press that'll go up to over 300 C in order to laminate it, get it to flow, and get a good fused bond. And it's more expensive than either the standard or the enhanced thermoset adhesive. Next question I'm going to ask is, what is your voltage supply? And the voltage supply is what's going to determine what metal we're going to want to use for your heater. For lower voltage applications, typically less than 50 volts, we look at whether we can use copper. That's going to be the least expensive way of doing it. We're basically going to build you a standard flex circuit where the traces are an element. And we can provide very good resistance density up to about ½ ounce thickness or less. The thinner the copper, of course, the more resistance we can pack into our traces. It's easy to process. It's readily available. The one drawback to copper, it works great if you have a fairly fairly small range of temperature you're operating. If you are going to a larger range of operating temps, the resistance will increase on copper as the temperature goes up, and so you'll have to have your control circuitry be able to compensate for that increase in resistance as the temperature increases. The next option would be Cupronickel 715 or Constantan. Both of these are copper nickel alloys. Cupronickel is about 70% nickel or 70% copper and 30% nickel. Constantan is about 55-45. They have very similar properties from a resistance standpoint. We typically use these up to about 125 volts. And all of these voltage numbers I have up here, there is a lot of blending. A lot of it depends on the size of the heater. For instance, if you have a much larger heater, we can use a lower resistance metal and still get the resistance that you need because they have more area to flood with the heating element. But for just standard size circuits, these are pretty good rules of thumb. So anyway, with the Cupronickel 715 or Constantan, we can get good resistance density. We have several thickness that we stock. It's easy to process. It is more expensive than copper. One nice thing about these copper nickel alloys is we can plate to them, copper plate to them. So we can actually go in, if you have like a flex tail coming out and you don't want that area to heat, we can copper plate those traces or specific areas that you don't want heat. And by putting that copper plating on top of the trace, it effectively lowers the resistance to the point where there's little to no heating that occurs there.
Mark, a couple questions. First of all, do we care if it's AC or DC?
The heater doesn't care one way or another. Either one of them is going to produce heat. One thing to keep in mind is that if you're using AC, you're putting AC into an antenna. And so if you have other electronic devices that are in close proximity, it might really drive them crazy. So most of the time we see these running at DC, but they can run at either AC or DC voltage. Either one will give you the heat that you need. It's just a matter if the rising and falling magnetic field from the AC is going to cause issues with other parts of your system.
Okay, and then the second one is, how do we calculate the resistance?
The resistance is, we have a resistance calculator that we use. We have CAD software where we can go through and figure out how many linear inches we're going to have on our traces. And we put it into our calculator and that'll spit out the trace width that we need. We're always looking to try and keep the traces. We like about a 50% coverage, 50% trace and 50% space. And we can vary from that depending on the watt density. But we like to try and keep the traces as wide as possible, because the wider the traces are, the tighter our resistance tolerance is going to be. When we etch these parts, the etch tolerance on very thick copper or cupronickel is going to be greater than it is on thinner coppers. And so if you look at a trace that's, let's say, 100 mils wide, if your etch tolerance is plus or minus 2 mils, that's basically a 4% variation. If your trace is only 20 mils and you have that same etch tolerance, it's more like 25%. So having a wider trace allows us to give you a tighter resistance tolerance. And so we typically look at weighing the size of the circuit, the shape of the circuit, and then pick the best alloy and thickness to give us the good, a good trace width and a good balance between trace and spacing. The other nice thing about the cupronickel alloys is that they have a very flat TCR, so that as the temperature increases, there's very little change in the resistance. And so your control circuitry doesn't have to drive them much harder to get a lot more heat out of them. Whereas with copper, as you drive them harder, they get hotter, and you have to continue driving them harder to get more power out of them. The last one we stock on a regular basis is Inconel 600. And this is typically used over 125 volts. It has a much higher resistance. And just as a kind of a point of reference, the cupronickel alloys, depending on which one you choose, it has either 25 or 30 times the resistance of copper. whereas the Inconel has about 60 times the resistance of copper. So we try and pick the best option there to give you the resistance density that you need and to get the power rating that you need with the voltage that you're going to be supplying to it. The issue with the Inconel, it is a bit more difficult to process. It's a very hard foil. It's more expensive than copper nickel. You do have limited termination options, mainly because it's virtually impossible to solder to it. We can do some soldering if we're using a pretty aggressive stainless steel flux, but even if we solder lead wires on with a very aggressive flux, we still typically need to pot over them with some type of a potting material that will anchor those pads and wires down so that they can't be tugged off. The Inconel also has a very flat TCR, so again, that will hold its resistance value very well as it goes across different temperature ranges. The next thing is, what type of heatsink is your flex circuit going to be bonded to? And that's, I guess, a good segue to talk about your power density. That's the number of watts you have per square inch. And this is really important to understand. And just as an example, you can have a couple of heaters. Let's take that heater that's in the upper right corner, and just for the sake of argument, let's say that is about 5 by 5 and it's 30 watts per square inch. Now, if I took two of those heaters and I put one of them on a piece of plastic in my office and put the other one on my welding table out in my driveway in Minnesota in January when it's 30 below zero with a nice light breeze, and powered them up to the same voltage, even though both are supplying the same amount of power, within a few seconds, the one in my office is going to start melting that piece of plastic and start smoking shortly after that. The one on the welding table would probably barely be discernible as far as the amount of heat that it's putting out. So you can have different applications. The application really drives how much watt density you can have and how much you need for what you're trying to heat. If you have higher operating temps, we typically want to have lower watt density. And if you look at the illustration to the right, you have to keep in mind that when these heat, if the nominal temperature of your heatsink is, let's say, 150 C, and you are in the middle of your heating cycle and ramping up to a higher temperature, those traces are going to be quite a bit higher than the mean temperature of the heatsink. Now, if the temperature of those traces gets above the maximum that the adhesive can handle, you're going to start delaminating those traces. And a lot of that has to do with the watt density. If you have high watt density, you have to make sure that your heatsink is able to pull the heat away fast enough so that you don't do any damage to the heater. If you have a low thermal conductivity material like plastic, you're going to need a lower watt density, and then it stands to reason because it's not going to be able to pull that heat away from your heat traces as quickly as something else would. One thing that we do, if you have a low thermal conductivity heat sink and we want to try and drive it a little bit harder than we normally would, we can put a foil backing on the heater. And this is a fairly inexpensive way of giving you a little bit more power rating on your heater, even though your heatsink isn't going to be able to pull it away as quickly. But that foil we put on will pull the heat away and spread it out over the entire area. So even the areas that are not covered by traces will be able to, you'll be able to conduct some of that heat into your heatsink. And so that's an inexpensive way to give yourself a little bit higher watt density on a heater that's on a low conductivity heatsink. And Chris went over the bonding method a little bit. PSA is probably makes up 80 to 90% of what we do. A lot of customers like to be able to install the heaters themselves, and it is a very effective way of doing it. You can get good heat transfer. There It will not be a void-free lamination. Those pressure-sensitive adhesives will leave small bubbles, and of course, a bubble is going to be that's going to be a little pocket where if it falls directly underneath the trace, it's going to be insulated, and you could end up with hot spots. So if you have a high watt density heater, you really don't want to go with pressure-sensitive adhesive. When we laminate with thermoset, we're typically doing that in hydraulic press, and when you're done, the finished product doesn't have any voids in it anywhere, so you can run those to a higher watt density. Now we're getting to cost drivers a little bit. As we talked about earlier, heater size and shape can have a big impact on the cost. If you have something that's very, very large, sometimes it's better to maybe go with 2 smaller heaters that will fit a little bit better. And I'm going to go into the way these are processed in a little bit. Since these are done on panels, we typically want to try and fit as many parts as we can on a panel and optimize, every square inch of space and throw as little into the garbage as possible for scrap. And if you have something that's very oddly shaped or that's very large, it's taking up a large chunk on the panel, it can have a huge impact. So just for discussion, let's call this panel a 12 by 24 inch panel, and it has a little bit of a perimeter around it. And this particular application is actually a flex circuit, but it's the same rules hold true for flexible heaters. So if I have a heater that I put on here and it's just slightly over the halfway mark, no matter how I panelize this, the best I'm going to be able to get is 4 parts per panel. Now, if I was able to shorten that by just a little bit, I can now get 8 parts per panel. Now, when you look at those parts, they look nearly identical. The parts on the left will be twice the price of the parts on the right. So panel density is very important. That's why I said if you have a very large circuit, in this particular case, if these were cut in half and you had 2 parallel heaters that covered the same area, it would probably be considerably less expensive than ordering just 1 large one. So that's something to keep in mind. And we can help steer you to that also. If we find an application where there's something that's a big cost driver, we'll typically try and flag that and give you some steering on how to design it better. Material selections, we talked about that a little bit. Everything kind of stacks on top of each other. If you're using the most expensive foil and you're using the most expensive adhesives, obviously it's going to drive the cost up as high as it'll go. So we typically will look at what you need for your application as far as temperature and your voltage requirements, and try and design it to give you the most cost-effective heating solution that will still be reliable in your application. And the heat bonding method, we talked about that a little bit. PSA is going to be, it's the least amount of processing to apply that. And so that's going to be the least expensive solution. And if you're using a thermosetting adhesive, because that's typically done in hydraulic press, that can be more complicated. It's typically something we have to do in our facility. And if you have a 3-dimensional object that you're attaching it to, that usually requires some fixturing also in order to properly adhere the heater. For termination methods, I would say that probably 75% of the heaters that we make use lead wires. That's the most common and it's the least expensive option. Those are typically soldered on whenever we can. The next one would be ZIF contacts. Those are very inexpensive options. Connectors are kind of all over the map based on the connector that you pick. It can be very expensive or they can be fairly inexpensive. But the only thing that we really can't do is solder connectors onto Inconel circuits, just because the soldering is it's very difficult and the solder just doesn't want to stick to it and you don't get a good bond. So we typically only will solder lead wires to Inconel circuits or use insulation displacement connectors to make those contacts. We just talked about the terminations. And again, you can see on the one on the far right here, how we've potted over those contacts or those solder joints, and that's really pretty common. We do that pretty much on all of them, but it's absolutely mandatory on Inconel circuits. On copper, it's mainly more of an insulation than a ruggedizing process. But on Inconel circuits, it's actually to ruggedize it and make sure that those don't peel off if those lead wires are pulled on.
Hey, Mark, hold on that slide for a second. So the image in the middle there has a little dot of epoxy to the right of the lead wires. There was a question that came through: what low height thermistor component would be suitable for flex heaters to avoid hand soldering? So typically, we put all kinds of components on both flex circuits and heaters that are pick and place, very, very small thermistors, readily available on DigiKey. There's a reference to a flat lead thermistor such as a B3950 NTC. I'm not familiar with this one in particular, but basically any component you could put on a rigid PCB, we can put on a flexible heater.
We do a lot of 402 and 201 NTCs. Those are probably the most common because they are very small. We typically do put a dot of epoxy over the top of them just to anchor them down so they don't move while the circuit or the heater is being handled.
Yeah, if you look at that image there, that dot of epoxy covering that component is probably less height than the lead wires.
Yeah, and you'll notice that on all three of these here, you're seeing 4 wires coming off, and that's, I would say that we have some type of temperature sensing that we put on virtually everything that we do. And the reason there's 4 wires is the 2 of those will be servicing your NTCs, and the other 2 are your power leads. So that's the most common way of doing it. And we do a lot of we do put a lot of components on our heaters. And that's all we have for our presentation today. So I'll turn it over to Katie, and if there's any additional questions.
All right, gentlemen, I'll pass it back over to you guys to grab some of these questions.
Okay. How are flexible heaters typically powered and controlled? So as Mark had described in that previous slide, the most common thing is where we have 4 lead wires coming off. 2 are for the NTC or thermistor, and 2 are actually powering the circuit hooked up to your power supply. And as Mark had mentioned, we want to make sure that we know what that voltage is going in so we can design the heater appropriately. Next one is, what advancements are being made in flexible heater technology? I don't know about you, Mark, but for me, I think the biggest thing is probably the temperature, operating temperature at which we can produce heaters now. So where you'll go back a decade or so, and typically that was at 125, 130 C. Now with these thermoplastic polyimides, we can get up to the 200 C. I mean, do you have any additional thoughts on that?
No, that's probably it. There's another question just came in. What are the disadvantages of directly soldered wire leads? Actually, there's no disadvantages. We do that on a pretty regular basis. The only drawback to leaving them open is if you have other metal objects that might come in contact, you could have a short. That's the only reason we pot to them, but we solder wires onto virtually all of our heaters. That's the most common way of making the connections.
There's one, do I need to lay out the trace pattern, or does FCT do that? So it can go either way. It seems like 98% of the designs at least I've seen, they come to us with either a resistance target or a wattage target provided with a voltage, and we design the circuit or the heater. It'll be an iterative process where we will design it based on the foil we think is most appropriate. But as Mark had mentioned, we're targeting a certain line width, which makes it more producible. And then we would provide that to the customer for approval. And they may come back and say, I want this area changed a little bit, or an adjustment needs to be made. But generally, we do the design on those.
Another question: if the power is larger than required, whether the flex fail safe? We can put fuses or thermostats directly onto the heaters. We can also etch fuses in. That's less common, but that is a possibility. That is a That would pretty much trash the system, though. You wouldn't, the heater's not going to be able to reset. They do have resettable fuses where they would shut off at a certain temperature and then reset when the temperature drops back down again. So those are probably the most common ways of putting the fail-safe in. The last one would be if you designed it with a copper, for instance, and we put a resistance in such that it actually, in your application, will top out at a certain temperature and just can't go any higher with the applied voltage.
All right. Does FCT check layout to make sure it makes sense according to design intent? So absolutely, that's one thing we pride ourselves in. As Katie and Ray had alluded to, our engineering team here all has 35 years or more of experience in flexible circuits and flexible heaters. So we absolutely do a design for manufacturability on your heater flexible circuit, and we will offer feedback on, if you consider doing this, it'll yield a better product, higher yielding, and you're going to end up with something more cost effective.
Another question here on about the size and cost concerns in automotive battery heating. They're very large and cost sensitive. Isn't that difficult? It's not difficult, but it can be expensive. And that's one of those things we'd look at the object that you're trying to heat. In this case, it'd be a battery. We have done battery heaters in the past, and in certain cases, to keep the cost down, you may heat just one side of the battery and then insulate that side so that you keep as much of your energy going into the battery as possible. Or you use multiple heaters to keep the heater smaller, so you don't have one large heater that's wrapping all the way around. You could have two smaller heaters that would cost a lot less.
Here's another one. Why use a profiled heater design? So typically speaking, the middle of your heater is going to get warmer. You can profile it such that you have a little higher watt density around the perimeter and kind of even out the whole heating area. So that would be one reason why somebody would want to use a profiled heater.
Another question on mil-aero industry. As far as stack-ups, your best guide there is probably the IPC specifications, both 2223, the flexible circuit design specification, and IPC 6013, that's the performance specification. And while these are basically heaters, they're also flexible circuits. It's just flexible circuits that have resistive elements in them. So all of the same requirements will cross over. And so that's probably your best resource during your design to keep it, if it works for a flex circuit, it'll probably work for a flex heater. And as far as the thermal qualities and performance and that type of thing, it's probably best to contact us and let us steer you on what you need to do to incorporate the thermal properties into the mechanical properties you've already gotten from the IPC specs.
And what variables need to be taken into consideration when figuring out what wattage is needed? So probably the big one there, as Mark had talked about, is just the environment that it's going to be used in. What's the operating temperature? What's your heat sink material? Is there a fan or a breeze going to be blowing on it? Those are all things you're going to want to take into consideration. And then, are you controlling it? You want to make sure you're not going to over-temp it. So if you are controlling it, you can err a little bit on the higher side as far as wattage, knowing that you're going to be able to turn this heater off when you reach your certain temperature.
And there are a lot of things that can affect how a heater performs, even the position that the heater is mounted. If you have a heater that's mounted vertically on a vertical surface, that heater is going to run hotter than one that's mounted on a horizontal surface, because you will not get the convection moving around the heater on a horizontal mounted heater that you would on a vertical heater. So if it's mounted vertically, you may need more power than if it's mounted horizontally. So there's a lot of things to take into account, and make sure that that's part of your design when you before you have anything built.
And to add on to that, how fast do you need it to get to your target temperature? So the quicker you need that to happen, the more wattage you're typically going to need.
Yeah, that's usually watt density. That's getting more watts per square inch to give you that fast heat up. And there's going to be a lag between the temperature of your heat sink and the temperature of your traces. And the better your heat sink is, the smaller that lag is going to be. And if you have a very, very, if you have a high wattage, high watt density heater, and you're ramping very, very quickly, if you don't have a heat sink that can pull it away, you may end up with that overheating over the traces themselves. And so in a perfect world, your control circuitry should be monitoring the temperature. And as you start approaching it, when you get up to maybe 75% of your target, it should be scaling back either through reduced voltage or duty cycle or something else to reduce the power to it. So you ease into that temperature. So when you actually hit your target temperature, there's zero power going to the heater.
What's the largest heater you can make?
Well, we're doing standard flex circuits that are about 1.5 meters long. And so we should be able to do a heater. The limiting factor there would probably be the width. We get all of our foils in 12-inch wide rolls. So out of that 12 inches, you're not going to be able to use the whole thing. You're going to have some border. So I would say that probably 10.5 inches is probably the maximum width. And then as far as length, we can probably go out to upwards of 5 feet in overall length. I have one here. What are the benefits of having aluminum backing? And we did discuss this briefly. It is a very inexpensive way. The aluminum that we put on is not very thick. It's only a couple of mils thick. So it's very inexpensive. It's an easy process. And that goes between your heat sink and your heating element. And that allows the heat to be spread out over a larger area. So instead of getting the conducted heat only through the spots where the element is in direct contact with the heat sink, you now have you essentially double the amount of area. If you have a 50% coverage between trace and space, it now gives you basically 100% of your heat sink coverage that's going to be conducting that heat.
One other advantage to aluminum is it helps hold shape. So if you're putting on a curved surface by pre-putting that aluminum backer on, it'll help hold that shape a little better.
Just Mark, one more just came in. What volumes can you do at your plants? And is there a minimum volume?
We service pretty much everybody. So, tens, hundreds, thousands. We have product that we build millions of pieces. So
our minimum order is 1.
Then our maximum is whatever you can dream up.
Yeah. Yeah. We have capacity that I dare anybody to try and fill it.
Mark, Chris, thank you. I would encourage anybody that has additional questions. There are quite a few we're not going to be able to get to today. Please reach out to Mark and Chris directly, and he and their teams will be happy to support.
All right, guys, thank you all so much. So Ray, Chris, Mark, thank you all for being here today and for answering some of our attendees' questions. It was great having you, and you guys did a great job today, so thank you. So I want to say a huge thank you to our presenters and for all of you for taking time to attend our webinar event today. Take care, and we will speak with all of you soon.